right, we are going to talk about the fundamental theorem of calculus. Interesting. Fundamental theorem of calculus. This is 6.4, fundamental theorem of calculus, and we talked a little bit about the fundamental theorem of calculus part 1 and part 2 in class last time we met, and I wanted to put a cartoon up here to lighten up the mood, and it says, describe in your own words the fundamental theorem of calculus, and this young man says, firstly, suppose that I got to get a college degree. Then suppose that I got to get take three calculus classes to get it. Here I am, QED. So he's only learning about the fundamental theorem of calculus because he needs it for college. So I suspect a lot of us fall in that boat, except for me, because I love it. And I'm a nerd, and you all know that already. So let's move on. Let's talk about it and do some applications. All right. So in our book, there is a funny quote, or at least I think it's funny, and it's my favorite quote of all time. And here it is. The Finny folks say, if you were being sent to a desert island and could take only one equation with you, the fundamental theorem of calculus part 1 equation would be the one to take. And we would say this as the derivative of an integral is equal to the function evaluated where you stop. That's the function you're finding the area under. So it's a pretty powerful theorem, and we're about to see why. All right, now we talked about this last time, that f prime was the derivative of an integral, the function evaluated where you stop. So let's see how it works. All right. So just then, some things to note here. First of all, this is a derivative of an integral, clearly. And this is an operator that says take the derivative of whatever's after it. And so we're taking the derivative of an integral. So that's clear. And then the thing you have to notice right away is when you're taking the derivative, you're taking the derivative with respect to x here. And you have to notice that it has to be a match up here on the top limit of the upper limit of integration with an x. So those two match, so we can keep going. And then we have to have our lower limit of integration be a constant, which is a in this case. And then we have a new variable here. Well, why is this a new variable? Because this is an area accumulation function in here, and I'm taking the area under this curve f of x starting at a, and what I'm trying to do is make my variable where I stop. And so that's why I have to use a dummy variable here, t, instead of x. All right. Now let's try an example here. Now I'm going to do this the long way, and we're going to work inside out, meaning we're going to find the antiderivative of the inside here, and then we'll take the derivative of this. All right. So what is the antiderivative of cosine? That means this is cosine is somebody's derivative. Whose derivative is cosine? Well, that's sine. And we're going to evaluate sine from negative pi to x. So that means we're going to put in x into sine and then subtract. This is big F of b minus big F of a. We plug these numbers in. And hopefully you all remember that the sine of negative pi is 0. All right. It goes to 0. And then I can take the derivative of sine, which is, voila, cosine. And if we recall what the fundamental theorem of calculus said, it said first, do I have a derivative of an integral? Well, the derivative of an integral, I do. Check. Do I have a limit of integration on top that matches with the respect to x? And the answer is yes. So I can keep going. And then the lower limit of integration is a constant. It is indeed, it's pi. And then I can take the derivative of an integral, and that's just the function I'm taking the area under, finding the area under, evaluated where I stop. So I take the cosine and plug an x in, and sure enough, this cosine equals this cosine. Now, with a show of hands, who would like to do it the short way versus the long way? Ah, I see. Everyone has raised their hand. Ha ha ha. All right, let's try another one. Here we go. Is this a derivative of the integral? The answer is yes. Because it's a derivative of an integral. Do the limit of upper limit of integration match the derivative with respect to x? The answer is yes. All right, and then the lower limit of integration is a constant. It is indeed, it's 0. And so we can say then the derivative of an integral is equal to the function you're finding the area under, evaluated where you stop. So you just take the x and you plug it in. All right, let's try another one. But wait, Mrs. Muller, what did you do? You changed this. This is no longer x. It's now function x squared. So I wonder what's going to happen here. All right. The upper limit of integration does not match the derivative, but we could use the chain rule. Oh gosh, yes, the chain rule never leaves us. It is with us everywhere we go. The beloved chain rule. All right, so the derivative of an integral is equal to the function you're finding the area under, evaluated where you stopped. Well, where did we stop? We happen to stop at x squared, but x squared has its own derivative, so we have to use the chain rule and take the derivative of x squared, and we get 2x. So the answer is 2x cosine x squared. Okay, what about this situation? Oh, Mrs. Muller, you've tripped us up again. Now the x is on the bottom. It's not on the top. Right? The lower limit of integration is no longer a constant. It's a function x. And the upper limit of integration is now a constant. But we learned something about the properties of integrals not too long ago, which says I can reverse the sign or reverse the limits of integration and flip the sign. So I can make this a negative and flip the limits of integration here. And now I'm going to ask you, do we have the derivative of an integral? The answer is yes. And do we have the constant as the lower limit of integration? The answer is yes. And now we can take the derivative of an integral, and that's just going to be equal to the function you're finding the area under, evaluated where you stopped, and you stopped at x. So we're going to put x here and x here. And then it has to be negative because we flipped and reversed the signs. Okay? Easy enough? Oh no, of course we've amped it up again. Not only do I have a function that's not x on top, but I have a function on the bottom. Oh no, what do we do? Well, this is what we do. We have to split the integral into two parts, theoretically, and we can choose an arbitrary number to split it apart. It doesn't matter what constant we use. So I'm just going to use 0 because that's a nice number. It really doesn't matter. I would not choose a number where the denominator is undefined, but then we have another issue altogether. But so now we can say, do we have a derivative of an integral? We do. A derivative of an integral. And is my lower limit of integration a constant? Yes. And I have a function on top here, but I can use the chain rule. And I can say, all right, well, the derivative of the first part is going to be 1 over 2 plus e to the x squared times the derivative of the exponent, which is, of the upper limit of integration, which is 2x. And minus, now I have to flip the sign here because I have to have the constant on the bottom. So that's going to be negative down here. And I'm going to do the same thing and plug the 2x into my function and then multiply times the derivative of the upper limit of integration, which turns out to be 2x over 2 plus e to the x squared minus 2 over 2 plus e to the 2x. And we are using the chain rule. Never goes away. All right. Now we talked about last time the second part of the fundamental theorem of calculus, which was the evaluation part. And if f is a continuous function on a closed interval, and f is the antiderivative, noting that this is the antiderivative, big F is the antiderivative of little f, then you can find the area under the curve by finding the antiderivative, evaluating it at b, and subtracting the antiderivative evaluated at a. And we talked about that last time. All right, and that's it. So let's do some examples. Some examples. I have a fundamental theorem of calculus packet that I put on Moodle for you to look at, and it happens to be this one. And I'm going to hopefully grab this, and well, it's not cooperating. Here we go. I want it to be huge. I want it to be like that. And then I want this to be like this, so we can see the packet and my working it out here. All right, so this is the fundamental theorem of calculus packet that I came up with. And my favorite quote is, "One does not simply drop the C," from the fundamental theorem of calculus. And, you know, that's Boromir there from Lord of the Rings. You know, he refers to one does not just walk into the city of Mordor. And that's obviously where that quote came from, for all of you Lord of the Rings nerds out there. All right, the fundamental theorem of calculus. I got this from your book, and you see that part one is the derivative of an integral is equal to a function evaluated where you stop. And the fundamental theorem of calculus part two is equal to, or states that the area under the curve is equal to the antiderivative evaluated at b minus the antiderivative evaluated at a. They call this the outvaluation part. I have been known on tests to ask you straight up what these two parts are. I don't care what order you list them, but it's important to know what those are, because it is, after all, the fundamental theorem of calculus, and we are putting the fun back into calculus, which is pretty cool. All right, so I have some examples here in this packet where I take the derivative of a function, or an integral function, where I have the one on the bottom and one on the top, that the limits of integration are not constants. And I show you how you can bust it up choosing a constant, and doesn't matter what constant. And you can also do the same thing effectively by evaluating the top minus evaluating the bottom. That's what it turns out to be anyway. Okay, so what I'd like to do first, because it's easier, is to do some evaluation parts here. So I'm going to flip to the page where it says Fundamental Theorem of Calculus Part 2 Practice, and hopefully expand this so we can all see it. All right, let's see here. All right, so what we're going to do is we're going to practice some of these, and I'm going to call this the Fundamental Theorem of Calculus Part 2 Practice. That's pretty small, so let's see if we can make it bigger. It's called adjusting in the middle of your video. Okay. All right, so let's try number one, because it's good to start at number one. This is the integral from 0 to 1 of 3x dx. All right, so this is somebody's derivative. We took the derivative of something and got 3x, so we need to find the antiderivative. Now the antiderivative, which is interesting, for x to the n, if we go the antiderivative of x to the n dx, now that's going to be equal to x to the n plus 1 divided by n plus 1 plus some constant we took the derivative of. Now, when we took the derivative of x to the n long ago, if I were going to take the derivative of x to the n, that would equal power down function, lower the power 1. We remember doing this. This is the easy part. We love that. That's the power rule. Well, we are going to do the reverse power rule. And instead of bringing the power down and lowering the power 1, we are going to raise the power up and then divide by the power because they are inverse operations. Okay, so in this case right here, we are going to raise the power up here. The power is currently 1. We're going to raise the power to 2 and divide by that power. So this is going to be 3x squared over 2 evaluated between 0 and 1. And we use the such that bar to show that we are going to evaluate this. And then we say, okay, well, that's going to equal, I put 1 in, so that's going to be 3 times 1, which is 3 halves, minus, and then I plug 0 in, and I get 0. So this integral is equal to this definite integral, 3 halves. Okay. Not too difficult. Moving right along. Let's do number 2. That's going to be the integral from negative 2 to 3 of x minus 5 dx. All right, so I'm going to do these antiderivatives a piece at a time, meaning, okay, so whose derivative is x? Well, this I'm going to use the reverse power rule to find the antiderivatives. I'm going to raise the power 1 to 2 and divide by the power, and we get x squared over 2. And what's really cool about this is that you could take the derivative of this, 2x divided by 2, and you see the 2's cancel and you get x. So if you take the derivative of what you finished with, you should get what you started with. All right, and so whose derivative is negative 5? Well, that's negative 5x. And we're going to take that and we're going to evaluate it between negative 2 and 3. And so let's do that. We plug the 3 in here. We get 9 over 2 minus 3 times 5 is 15. And then we're going to subtract the antiderivative evaluated at negative 2. So that's going to be 4 over 2, which is 2, plus 10 because the negatives cancel. And let's see what we get here. We get 9 halves minus 30 halves. And this is going to be minus 12, which is minus 24 halves. And that's going to be 54, negative 54 plus 9, which is negative 45 halves. All right. So one more. Let's do number 3. This is the antiderivative from negative 1 to 4. I can recover. Of x squared plus 2x minus 1. And then we're going to find the antiderivative of each piece. In order to do that, I'm going to raise the power 1 here and divide by the power. So this will be x to the 3rd divided by 3 plus, raising the power 1 here, we get x squared over 2 times 2, which is just x squared, minus x, evaluated between negative 1 and 4. And so let's plug 4 in here, and we get 64, because 4 cubed is 64, over 3, plus 16, minus 4. And now we're going to plug in the lower limit of integration, and we're going to get negative 1 cubed is negative 1 over 3, plus 1. And then if I plug a minus 1 into a negative number, we're going to get a plus 1. All right. And simplifying this, we get 64 over 3 plus, that's going to be 12. And 12 times 3 is 36. So it'll be 36 thirds. Minus, this is going to be 2 minus a third. So 2 minus a third. So 2 is 6 thirds. Minus 1 third is 5 thirds. So this is minus 5 thirds. So that's going to be 64 plus 36 minus 5, which is 95 thirds. Now, we can check my math here, which would be really good to do by using our handy dandy calculator. So let's practice some integrating using the calculator. I happen to have mine ready to go here. Okay. I don't know if you can see that. So I'm going to go home. Ha ha ha. And in order to do this, I'm going to zoom in just a little bit because I can. All right, in order to integrate this, we're going to go first of all, I want to integrate this one here to see if we're right. Okay, so in order to do that, I'm going to hit F3, integrate. And I'm going to type in x to the, and I'm going to go alpha n, which is above the 6, comma, and then x. And then I'm going to close that and see if it'll give me the antiderivative. Lo and behold, it did. How cool is that, that our calculator can do that, even with variables? All right, now let's do number 1 on the calculator. So we'll say second, F3 integrate, which is number 2. And we can say the integral of, well, what is our function? It's 3x. We're going to type in 3x, comma, I have to tell it what the variable is, which is x, comma, 0, comma, 1. Close the integral. There it is. It's 3/2. We were right. And if we wanted to see if our antiderivative was right, all we would have to do is take off the limits of integration here, and your calculator will integrate it for you and see if you're right. So that's pretty cool. All right, moving right along. Let's do number 2. And let's see if we got that answer right. It's not very pretty. I'm sure you guys have already seen an error if I've done it. But let's try. So this, and there's a hotkey here. If you look at your calculator pretty closely, if you hit the second button and above the number 7, you'll see a little integral. So I'm going to use second number 7. I call that the Joe Calpin key because he showed me how to do that many years ago. And I'm making him famous now. All right, so what's our function? It's x minus 5. So we're going to type in x minus 5. And then we're going to go comma the variable x. And I'm going to close this just to see if my antiderivative was right. I said x squared over 2 minus 5x. And there it is. We were right. And now I'm going to hop down here and put in the limits of integration, which were comma -2, comma 3. My fingers are crossed. Negative 45 over 2. We were right. Good news. All right, number 3. All right, here we go. We're going to go second number 7, which gives us a nice integral key, and we're going to type in x to the second plus 2x minus 1, comma x, and I'm going to see if my antiderivative was correct, and we get x to the third plus x squared minus x, and that's awesome. We got that right, and now we're going to just put in our limits of integration. So this is going to be comma -1, comma 4, close the parentheses, and then press enter, and we got 95/3, which is not a pretty number, but as you can see is correct. All right, so I just wanted to do a few of those. Actually, I'm looking now down the list, and I'm liking number 7, because that might look scary to some folks, but it's not really. So let's do number 7 together. All right, number 7. That's the integral from 1 to 9 of 2, or x minus 2, sorry. Helps if I can read. X minus 2 over the square root of x dx. Now that might not look like something that we can find the antiderivative of, but we can actually bust this up a little bit, this integral. And we can say, all right, well, this equals the integral from 1 to 9 of x over the square root of x minus 2 over the square root of x dx. All right, and when we do that, we can get the integral from 1 to 9 of, this is x over the square root of x. which is just, if I subtract the exponents, that's 1 minus a half. So that's going to be x to the 1/2 minus 2x to the, and I can make this a negative exponent, negative 1/2. Oops, negative 1/2. And now I can use the reverse power rule here to find the antiderivative. So I'm going to do that. I'm going to say x to the, now when I add 1 to 1/2, that's going to be adding 2 over 2. So 1/2 plus 2 over 2 is 3/2. And so now I have to divide by 3/2. So if I have a number and I'm dividing by 3/2, that's the same thing as multiplying by 2/3 when I flip the denominator. So this is going to be 2/3 x to the 3/2. So you always, if you have a fractional exponent, you flip it when you multiply it in front. Okay, so minus 2 times x to the, well, let's raise it the negative 1/2 by 1. So I'm going to add 2 over 2 to that exponent and get to the 1/2. And then when I flip the 1/2, I get times 2. So we're going to put a 2 here. Evaluated between 1 and 9. Okay, so that'll be 2/3 x to the 3/2. And this will be minus 4x to the 1/2. Still evaluated between 1 and 9. I just wanted to make it in a nicer format. Okay, so let's plug in 9. So 9 to the 3/2. When you take the 9 to the 3/2, I always do the root first because it makes it smaller. So the square root of 9 is 3. 3 cubed is 27. So 2 times 27 over 3 minus, I'll put 9 in here. The square root of 9 is 3. So that's going to be negative 4 times 3. All right, and now we're going to plug in the other part, the lower limit of integration. So that'll be 2/3, which 1's very nice, minus 4. Because the square root of anything is of 1 is just 1. All right. So then this is going to be, this reduces to 9 here. So that's going to be 18 minus 12 minus 12 and thirds is, 4 and thirds is 12/3. You see, my brain was already doing that. So we're going to have 2/3 minus 12/3, which is 4. So that's going to be negative 10/3. So let's do some math here. This is going to be 6 minus, you guys are watching the painful addition in my head here. This is going to be negative 10/3 because that is indeed 4. All right, and then I'm going to add, this is 18/3 plus 10/3 equals 28/3. Woo! Wow. All right. Now let's see if we are right using the calculator. Second integrate, which is number 7. I'm going to put the original in there. I'm going to use parentheses for the numerator. X minus 2, close parentheses, divided by second square root of x, close the square root, divide, comma, x, comma, 1, comma, 9. Oh, there we go, 28/3. That's good news because I'm doing this live and haven't practiced this. So we're going good so far this morning. All right, that's number 7. Let's see what another one that I like here. Oh, yes, I like number 10. Because I think you can do the other ones here. All right, so number 10 is the integral from 0 to 3 of the absolute value of x minus 2. Now, whenever you see the absolute value, you must be thinking, oh gosh, it's going to make me change this to a piecewise, which I appreciate that fact because I do like it when you change them to piecewise. And you could theoretically do that. But whenever I see a piecewise function, I go back to the day where I remember geometry fondly, which isn't very often. No, I like geometry, but you know, I wasn't necessarily very good at it. So here we go. This is 2. And we know that our absolute value function is going to look like this because it has a slope of 1. So I'm going to have 1 and negative 1 here. All right. So I always go back to the graph when I'm integrating or finding the antiderivatives of, or the definite integrals of absolute value. And we're going to go from 0 to 3. So 0, to 3. And that's nothing more than the area under this curve, which is 2 triangles. All right, so this is going to equal 1/2 the base here, which is 2, times the height, which, believe it or not, is 2, plus 1/2 the base here is 1, times the height here is, when I plug 3 in here, I get 1. So that's going to be 4/2 plus 1/2, which is 5/2, is the antiderivative here. And we can prove it to ourselves. Remember, we're using our fancy dancy calculator, and we can go second integrate, and I'm going to use the absolute value here. And how do we do that? We go alpha A, alpha B, alpha S, which is above the number 3, parentheses x minus 2, close parentheses on the absolute value, comma x, comma 0, comma 3, close parentheses. And we get 5/2. Now, I just want to refresh your memory, too, on the fact that we could go to y equals. Now, the nice thing about this calculator is I can copy and paste. So I'm going to get rid of all these other things here. And I'm going to press enter. Okay, and I'm going to come up here and I'm going to grab it by hitting the copy button, diamond copy. And I'm going to go to y equals, and oops, I'm in differential equations mode. Oh, so let's change that to function mode. Sorry, you guys won't have to do that, but I have to do that. All right, I'm going to clear this out. I'm going to go diamond paste, and there it is. There's my absolute value of x minus 2. And I'm going to go check my window here because my window might be a little bit weird. No, well, it looks pretty good. Diamond graph. There's my absolute value function. And we remember, right, how to find the area under the curve using our calculator. We go to F5 and do some math, which will be number 7. And the lower limit of integration here was 0. And I'm going to press enter. And the upper limit of integration is 3. So let's plug 3 in. And it will actually draw it for us and tell us it's 2.5, which is 5/2. So we win the prize. Okay, all right, so I've shown you how to do that 2 ways. And now I would like to do some AP Calculus free response type questions that are also in this packet. And I want to do 2 of them, and then I'm going to do a couple of multiple choice so you can see where we're headed with the fundamental theorem of calculus. All right, so I'm going to do 2012, number 3, which happens to be the first one in this packet. Okay. And let's see here. I actually have a hard copy of this so that I can draw on it, so you can see what I'm doing. Sorry, my fingers aren't working today. Okay, here we go. Here's my hard copy of the graph. I should have been more ready, but there we go. There's my hard copy of the graph. Okay. There we go, because I want to be able to write all over this. Okay, so part A states in this problem, let f be a continuous function defined on the interval from -4 to 3. So here's f. This is continuous, which we know what that looks like, whose graph consisting of 3 line segments and a semicircle centered at the origin is given above. Let g be the function given by the integral from 1 to x of f of t dt. So right away, they're telling us that g of x is equal to the integral from 1 to x of f of t dt. And now some bells and whistles I hope are going off, because this means this is an area accumulation function. Because where am I accumulating area from? Well, I'm starting at 1, and I like to, on my graphs of these, actually put like a little dashed line, really quietly dashed, to know where I'm starting to find the area. Okay, so I'm starting to find the area at 1. Okay, so that's just for future reference. Now, part A says we need to find g of 2. Well, let's see what g of 2 is. Well, g of 2 is nothing more than the integral from, because I'm going to plug in 2 where the x is, from 1 to 2 of f of t dt. Now, what does this mean theoretically? It physically means I need the area under this curve from 1 to 2. So from 1 to 2, right there, that's the area I need. So how do we figure that out? Well, we got to see maybe the equation of the line there. Well, this is 3, negative 1. And what is the slope of this line? The slope of this line is going to be 1 over 2. Do you see how the slope is going to be 0 minus a minus 1, which is 1, over 1 minus 3. So the slope of this line is negative 1/2. So if it's negative 1/2, then we know that this point here is going to be 2 1/2. Okay, so I know that that's going to equal the area of that triangle, which will be 1/2 its base, which is 1, times its height, which is 1/2. So that g of 2 is 1/4. Okay, so that's, we're lucky. We got g of 2 equals 1/4. Good news. 1 point so far out of our points here. Now they want g of negative 2. Well, that's just the integral from 1 to negative 2 of f of t dt. Now let's think about this. This is the integral from 1, starting at 1, going to negative 2 over here. 1 to negative 2. So that's going backwards. So I'm going to say that this is equal to the negative integral from negative 2 to 1 using my properties of integrals. And now I'm going to start computing area. Now I'm going to start here at negative 2, and I'm going to go forward to 1. All right, so it's going to be negative times, well, the first shape here is a triangle, which has, so it's going to be 1/2 its base, which is 1, times its height. And they told us that the height is at negative 2, 3. So we're going to put a 3 here. Okay. Now, what's going on here? This right here is a semicircle. This is a semicircle. And its radius is 1. So this area here is going to be pi r squared over 2 because it's a semicircle. And this area here is pi over 2. Now, we said that this is going to be 3/2 here. Now, I don't put any of the signs on here when I'm doing these because I let this dictate what the signs are. Now, this is below, so this is going to be minus pi over 2. So it's going to be 3/2 minus pi over 2. But I'm going to have to be doing a subtraction here. So I'm going to distribute this negative. So I'm really going to get pi over 2 minus 3/2. So g of negative 2 is equal to pi over 2 minus 3/2. Okay, that's part A. Part B. I'm going to get onto another sheet of paper here. Part B. Part B states, for each of g prime of negative 3 and g double prime of negative 3, find the value or state it does not exist. All right, well, so we need g prime of x. So what does g prime of x equal? G prime of x equals, well, gosh, it's the derivative of an integral. Looks like the fundamental theorem of calculus. Okay, so if this is the derivative of an integral, we're going to go over really quickly. Well, does the upper limit of integration match the lower derivative with respect to x? The answer is yes. And is this a constant? Yes. Well, the derivative of an integral is just equal to the function you're finding the area under, evaluate where you stop. So this is just f of x. So g prime of x is equal to f of x. And I need g prime of negative 3. So I need f of 3. Well, what is f of 3? Well, I'm just going to go over here and see if I have a value for f of 3. And I need negative 3, sorry. F of negative 3. F of negative 3. So 1, 2, 3. I need this value here, which looks like it's 2. So g prime of negative 3 is equal to 2. Now I know for a fact that you get points for writing this expression here. So that's really important, okay? Now we need g double prime of x. Well, g double prime of x is just the derivative of g prime. And the derivative of g prime is equal to the derivative of this, which is f prime of x. Well, what is f prime of x? Well, f prime of x is the derivative of f, and this is f. So the derivative of f is actually the slopes of this function. So I just need the slope at negative 3. So this will be g double prime of negative 3, which is equal to f prime of negative 3, which happens to be the slope of this function at negative 3. And if we were to do the slope of this, it would be 3 minus 1. I'll do it with you. 3 minus 1 over negative 2 minus a minus 4. So this will equal 2 over 2, which happens to be 1. So g double prime of negative 3 is equal to 1. Now, a g double prime of negative 2 would not exist because that's a corner. And the limit of the slope to the left and the limit of the slope to the right, they don't equal each other. So that wouldn't exist. But they both exist here. So we've done that, part B. Pretty good. All right, let's do part C. Part C. All right, part C says find the x-coordinate of each point at which the graph has a horizontal tangent line. All right, so this graph G has a horizontal tangent line somewhere. All right, so I like to do a sign chart. So we're going to do a sign chart. So G is going to have, so I'm going to write this down. C, G of x has horizontal tangent lines when G prime of x, which we figured out earlier was equal to f of x, is equal to 0. So let's do a G prime equals f sign chart. So here it is. Here's our sign chart. And I'm just looking at this. Now, when is f equal to 0? F is equal to 0 at, looks like negative 1. Because I get lost in this pretty graph here. So I like to do a sign chart independent. And then this is 1 here. And these are zeros. And then what is the sign of f here in between? Well, it's positive. And I've got an endpoint here of negative 4 and an endpoint here of 3. So we have positive y values on f from 0 or negative 4 to negative 1. And then from negative 1 to 1, we have negative. And we have negative values after that. Okay, so we have horizontal tangent lines at x equals negative 1 and 1. And they want to know at each one of these locations, we have to determine whether we have an absolute or we have to have a relative min or relative maximum or neither at the points. So we can say at x equals 1, right? Because we can do our little dance here. We know we have what here? A relative max. And here we have a negative slope to 0, slope to negative. So we have a big fat nothing there, nothing burger. Okay, so this is going to be relative, I should say G has a relative because that's what we're addressing. G of X has a relative max at X equals 1, since, I can put my justification here, since, how did we know that using calculus? Well, we knew that G prime of X was greater than 0 and then went to G prime of X is less than 0 at X equals 1. Well, at X equals -1, G of X has neither a max or a min, since G prime of X does not change signs. And that would be our justification there. Okay, so that's part C. And that's worth 3 points there, so that's good. Part D. Part D. Part D states, for the open interval from -4 to 3, find all the values of X for which G has a point of inflection. Explain your reasoning. Okay, so points of inflection occur when G double prime of X changes signs. Okay, now it's not enough for it to equal 0 or to be undefined. It has to change signs. Now let's talk about what is G prime double prime of X. Well, G double prime of X, we stated earlier, was just F prime of X. So I need to know when the slope of F, of the tangent lines to F, changes signs. Okay, so I'm going to do a sign chart for G double prime. Okay, which is equal to F prime. From -4 to 3. Now, the slope on this line here is positive, right? So that means at net, that's -2, I think, not -2. We're going to put -2 here. And that's undefined there because that's a corner. But it's got a positive slope on the left side of that one, and it's got a negative slope to the right of that one. Now, this doesn't change slope signs. This is a positive slope. This is, negative slope, negative slope, negative slope. Oh, I have a 0 slope here, and that's at 0. So I have a 0 slope at 0. And then I go from negative tangent line slopes to positive tangent line slopes until I get to 1. So I have positive tangent line slopes at 1. And then I have an undefined situation because I have a corner, or a cusp corner. And then after 1, I have negative slopes. Okay, so where does G double prime or F prime of X change signs? Well, clearly it changes signs at X equals -2. So we can say at X equals -2, where else does it change signs? At 0. And it changes at 1. We can say G of X has points of inflection since G double prime of X changes signs. And we're done with part D. And that's 2 points. You get 2 points. You get 1 for the -2, 0, 1, and for the explanation. So good. That's 2012. All right. Now, I was going to do 2017, but I think I'm going to hold off on 2017. And let's do a couple of multiple choice so we can finish up for today. Moving right along in this packet, here is the multiple choice. All right, so let's do number 69. From the problem from 1969. See, I went and I just got the most, I started from the earliest renditions that I had here. So this is number 1, which is from 1969, and it's actually problem number BC 12. So we're going to be doing a BC problem. But the BC problems were also on the AP exam. There was some crossover. Okay, so they're telling us if f of x is equal to the integral from 0 to x of e to the negative, that says negative t squared dt, then we need to find f prime of x. Well, we should be able to do this. It's pretty easy because we are going to be taking the derivative of an integral. And we know by the fundamental theorem of calculus part 1 that if the derivative of an integral, which is what we have, and we have with respect to x and the upper limit of integration is also x, we can say that this is equal to the function evaluated where we stop. So it's going to be e to the negative x squared evaluated where we stop, which is pretty cool. So there it is. So the answer should be, in this case, E. All right, so that's 1969 BC 12. All right, so let's look at number 2 because that looks a little bit more interesting. This is 1969 BC number 22. Okay, so that question states if f of x is equal to the integral from 0 to x of 1 over t cubed plus 2, the square root of t cubed plus 2 dt, which of the following is false? We all love those. Okay, f of 0 is equal to 0. So let's see what happens. When we plug in 0, the integral, this is f of 0, is going to equal the integral from 0 to 0 of 1 over square root of t cubed plus 2 dt. Well, guess what, folks? That is 0, right? Because we're going from 0 to 0. There's no area under that curve. So A is true. Okay, so part B says f is continuous for all values greater than or equal to 0. Now, this is an area accumulation function, and I don't have any discontinuities in this, because if I were to have a discontinuity, it'd be when t cubed plus 2 equals 0. T cubed plus 0, t cubed equals negative 2. T equals negative cube root of 2. So I'm going to have a discontinuity when t equals the negative cube root of 2, which is not in the domain of this one. Let's see, can x be the negative cube root of 2? Hold on. Well, hang on this one. We're going to keep going. F of 1 is greater than 0. This function here is always positive under here. So f of 1 is equal to the integral from 0 to 1 of 1 over the square root of t cubed plus 2 dt. So this value, when I plug 1 in, is going to be positive. When I plug 0 in, it'll be, I'm finding the area under a positive curve, so it's going to be positive. So this is greater than 0. This is true. Okay. F prime of 1. So what is f prime? Well, f prime of x is equal to the derivative of an integral from 0 to x of 1 over the square root of t cubed plus 2 dt. And if I take the derivative of that, that's just going to be f of x, or, I take this and I put the x in it. So it's going to be the square root of x cubed plus 2. And f prime of 1 is going to equal 1 over the square root of 3, which is true. So this is A, this is B, which we're still thinking about. This is C, And this is D, which is true. And E, f of -1. Let's think about that. That's going to be equal to the integral from 0 to -1 of 1 over the square root of t cubed plus 2 dt. Now, that's going to equal negative the area from -1 to 0 of 1 over square root of t cubed plus 2 dt, because we have to, you know, flip the sign there. And I think the answer is, this is negative. The cube root of 2. Let's see here. What is the cube root of 2? Let's figure that out. Second quit. Go home and clear. I'm going to go 2 to the 1 divided by 3 diamond. That's 1 point something. And this is always going to be positive. You know, this is 1 over the square root of something. So it's always going to be positive. So I think this one is false, because this is a positive area and we're making it negative. Okay. And this one, this one is true. Oh, it's for all x greater than 0. Sorry, I didn't know. I didn't notice it said for all x greater than or equal to 0. Yes, that's true, because obviously the discontinuity is going to occur right here. So this is clearly true. I'm sorry, I missed that part of that question. And then that one's false. So gosh, this one is E also. I guess maybe all the questions in 1969 were E. All right, I just wanted to do a couple of multiple choice. I wanted to do an example free response and several of the evaluation parts of the fundamental theorem of calculus. And that's all I have for today, thankfully. Have a great day.